Hey there, welcome back to Real Analysis. We're going to continue our work in Chapter 2 on sequences of real numbers. Today in Section 2.7, taking a look at what the author calls algebraic properties of limits, or in calculus, you probably called these things limit laws. Proving limit statements with the epsilon n definition can be algebraically tedious, very difficult to nearly impossible, if the sequence terms themselves are sort of very complicated algebraic expressions in terms of the index n. Right? So in other words, finding that capital N in terms of epsilon, in the examples that we've looked at in the homework and in lecture, we were able to do it. But if we started writing down more algebraically complicated expressions, determining that N in terms of epsilon would be difficult. So what I want to do is develop some tools that allow us to compute limits without always going back to that first principle. So we'll use that epsilon n definition to develop these tools, but then we can just use the tools to compute limits. You're going to be used to it because you've done this stuff in your calculus courses. So in particular, in this first go around, what does the author mean by algebraic properties? Well, we're going to be looking at combining sequences with the four arithmetic operations: addition, subtraction, multiplication, and division. How can we do those things to sequences? Well, sequences are just functions from the natural numbers to the real numbers. And functions can be added, subtracted, multiplied, and divided. Division requiring, of course, that the output of the denominator function is never zero. So since you can do those arithmetic operations to functions, you can do them to sequences. And the kind of material I want to talk about with you in this lecture is like, okay, well, suppose I've got a couple of sequences and I know that they converge. I know their limits. What can I say about the sum of them, the difference of them, the product of them, the quotient of them? Right? So these are the algebraic properties I want to develop. This video is going to be maybe a little long. So I'll just tell you that right now, and you can always kind of stop it, maybe watch it in chunks. But instead of kind of breaking it up into several videos, I've decided just to see if I can concentrate long enough to muscle through all this material. All right. Some of the proofs, every one of the theorems I'm going to present here in this video are written in your book, but the author doesn't kind of include what we've been calling the discussion section of the proof, the kind of back room, where do the details come from? So I'm going to include those discussions. In some cases, I'm just going to talk about the discussion and then kind of kick you over to write the formal proof or read the formal proof in your book. But in a couple of the cases, I'll do both. We'll have the discussion and write the formal proof. Okay, so let's get going. Let's start with our terminology and notation. So let's give ourselves a couple of sequences. I'm going to use the same notation as the author in this section. So they're going to be called S and T. So their terms are called S sub n and Tn. Their sequences of real numbers. Also, let's pick some real number, a constant C. So it's a number that's fixed. And then we're going to define some new sequences. We're going to define some new sequences. Here on the left-hand side of these equality signs, I'm writing what the sequences names are. So C times S, S plus or minus T, S times T, S over T. Then in the set braces notation, I'm writing just in the term notation. So C sub S sub n, S plus T sub n, and so on. Okay, I won't try to say it all. My tongue will start tripping. And then on the right-hand side, the last kind of column, if you like, in my little table here, I'm giving an explicit formula. So what is the nth term of the sequence CS? Well, it's just C times the nth term of S. So you multiply a sequence by a constant means you multiply every one of its terms by that constant. Same thing with plus or minus, the nth term of S plus or minus T. Well, you take Sn and Tn and you add or subtract them together. Multiplication, division. Okay, this last one certainly requires, I think I've already written it here. Yeah, so let me just scroll, that the values of T sub n cannot be zero for all n. So if you're going to divide by a sequence called T, it has to be the case that no one of its terms can be zero. Because if so much as one term is zero, then at some point you're going to be writing Sn over zero, and that's not defined. There is no real number that would equal something divided by zero. Okay, so these are our arithmetic operations, and we'll just refer to them the same way we do numbers. We'll call this a constant multiple of a sequence, the sum or difference of sequences, the product of sequence, the quotient of sequences. Nice. So the first theorem deals with that first construction, constant multiples. So let's parse out the statement of the theorem and then look at the discussion that I've kind of pre-written out here. So we'll take that sequence Sn written above, and we'll take our real number C. The author's writing it as a capital. That's fine. Maybe I was writing it at capital above too. So we've got a sequence called Sn and a real number. And then what the statement is, and this should look familiar from calculus, that the limit of the term C times S sub n, the sequence that's the constant multiple of C times our sequence S, is C times the limit of S. Here I'm assuming that S is a convergent sequence. Okay, so calculus students usually say something like you can pull a constant through the limit. Yeah, that's how this thing is usually referred to in calculus classes. So here our business is to prove that. We're going to give a rigorous proof of that fact. Maybe you had a great calculus course and you gave a rigorous proof of it there. You certainly could have handled it, but let's see if we can't say something about it here. So before we jump into the proof proper, I kind of want to have the backroom discussion here because, these analysis proofs, when you write them sort of elegantly and compactly, lots of kind of background work was done to discover what kind of choices we have to make along the way in the proof. So in this first theorem, 2.14, which we'll just refer to as multiples and limits or the constant multiple rule, I want to show you that background. So for some notation, let's call the limit of Sn S. Okay, I'll do this throughout the entire lecture. So my sequence Sn approaches S. And what do I mean by that limit? It means that if I'm given some number epsilon, I can make the sequence terms differ from the limit S by less than epsilon if n is big enough. Right, so more precisely, if there's some capital N, so that this difference would be less than epsilon for all n bigger than n. I'm just going to kind of colloquially say that if n is sufficiently large, then this difference is small. Okay, I want to show, I'm trying to prove the statement about the constant times S, C times S. So what am I trying to show is that this difference of CSn minus CS is small for sufficiently large n, right? But by a little bit of algebra, if you factor the C out of that expression and use a property of absolute values, I get that expression. I'm going to kind of look at some cases. If the number C is equal to 0, well, then you just obliterate this sequence when you multiply all of its terms by 0. You get a constant sequence that's all whose terms are 0. C times the limit would also be 0. And of course, this is small for any n because this thing is just 0 minus 0. Well, that's going to be less than epsilon for any epsilon, and that's starting with n equal to 1. So if C is equal to 0, we're going to get what we want immediately. If C isn't 0, I'm going to return to our last line up here and divide both sides by C. That probably tells you why I was worried about C not being 0. The absolute value of C isn't 0 either. So what do I need? I need the difference of Sn minus S to be less than epsilon over C for sufficiently large n. If I could get that, for sufficiently large n, if I could get this, then I would have the previous condition by multiplying by C, which would give me what I want. All right, maybe stop the video right now and write your own proof. I'll bet you can do it. I'm going to just continue on here. I'm not going to do any dramatic pausing because it makes the video too long. But so with that all rattling around in my head, here's what I wrote. And even this, I want to say to you guys, it wasn't my first draft. I had to kind of adjust around a little bit because I'm trying to make this sort of compact and elegant, but let's see if you think I succeeded. So my proof is, and I'm trying to kind of illustrate good habits here. So I quantify everything. So let's let this Sn be my sequence of real numbers and C be a real number. Everything's quantified so the reader knows what I'm talking about. And then let's state our hypothesis. Let's suppose that this sequence converges to S. Okay. This is going to be a limit proof, so I want to make sure the reader knows that I'm letting epsilon be an arbitrary positive number. So I write it. It's a complete sentence. Let epsilon be greater than 0. And then I'm going to do away with that trivial case. If C is equal to 0, then, well, anything times 0 is, oops, pardon me, I'm missing an S there, is 0. So no matter what n is, in particular, you can just take any n greater than or equal to 1. This difference is just 0 minus 0. It's less than epsilon. So our sequence converges in that case. All right, so that's a kind of a trivial case. If you multiply everything by 0, everything is equal to 0. So for the rest of my proof, I'm going to assume C is not 0. And now using the fact that Sn converges to S, I know that given our epsilon that we quantified above, I can find some capital N so that when n is bigger than it, my sequence terms differ from S by less than epsilon over C. That doesn't feel like it's out of left field now because you know where I'm going with this, why I chose epsilon over the absolute value of C and not just epsilon. It's because we know that after we do the algebra, we're going to get what we want. Okay, so if we take n bigger than that capital N, let's just run through the algebra. Our sequence terms, CSN, differ from CS. Well, by algebra, I can factor out that C with the absolute value. And now I'm using the fact that the difference of Sn and S is less than epsilon over C because n is large enough. But epsilon over C times C, I'm not pronouncing the absolute values, but you can see them, is epsilon. So by definition, this sequence converges. Definition of limit, the epsilon n definition, or definition 2.6. Nice. Stop the video, mull it over. Maybe that's the proof you wrote. I hope it is. I'm just going to keep going here so that this thing is not unnecessarily long. So the next one handles sums and differences. I'm only going to talk about sums in this video. I'm going to leave the differences. I think it actually might literally be one of your exercises in your homework. I can't remember right now, but I'm not going to talk about differences, but you can just make the appropriate changes. So let's start with the discussion. Okay, so I'm just going to talk about sum here, or leave differences to you. Going to be a little briefer in my notation here because I think I've established the spirit of this. So we got these two sequences, Sn and Tn, and let's suppose that Sn goes to S and Tn goes to T. Nice notation. So if you give me some target, some positive epsilon, I want my sequence terms, Sn plus Tn, to differ from the sum of the limits by less than epsilon. I want that to be true if n is big enough. So now I'm fishing around, I'm playing around algebraically with my want, my wish, to see, well, how big is big enough? Okay, well, let's rearrange that a little bit, to distribute that minus sign and regroup the terms. I would need that to be true. But by the triangle inequality, this sum that I'm highlighting, I'm not going to try to pronounce it out loud because it starts to sound too difficult. But by that sum I just highlighted by the triangle inequality is less than or equal to the sum of the absolute values added together. All right, so it would be good enough if we could show that these two things themselves were getting small as if n was sufficiently large. These are the two terms that I quote unquote want to control. So I've written that down by it suffices to show that this sum is less than epsilon. All right, but we can control these things, right? I can make Sn as close to S as I want. I could make it within epsilon. Since I have two terms, I'm going to just try to motivate what I'm doing down here. If I pick n big enough, because Sn goes to S, I could make that S difference less than half epsilon. The half's not random. It's because I have two terms here. I'm trying to make their sum small. So I'll make each one of them half of epsilon. And when I add them together, I'll get an epsilon, right? That's going to be true if n is big enough that n1, it's because it's the S sequence. Maybe you want to call it like n sub S or something like that. But likewise, Tn goes to T, so the T difference could be less than half of epsilon if n is big enough. How big it is for T and how big it is for S, they're probably not the same. That's why I'm not using the same n, right? Given this target, epsilon over 2, S tells me how far out to go. T tells me how far out to go. I don't expect those things to be the same. I mean, they might be. I don't know. I might luck out, but they might not be the same. I don't expect it, but I don't care, right? Because as long as I go out past both of them, then those inequalities would be true. So I take n to be the bigger of the two. I don't know which one is bigger, but I don't care. I just let n be the bigger of the two. And then if I take n greater than or equal to capital N, then both of these conditions hold. All right. So what would it mean? It would mean that this term is less than epsilon over 2. Simultaneously, this term is less than epsilon over 2. So their sum is less than epsilon. Okay, so this one I'm going to leave the formal proof right up to you. It's also written in your text, but I think it's kind of a fun thing to do, and I think it's going to be a more meaningful experience for you if you try to write it up yourself before looking at the author's write-up in the text. All right? So try that, then look at the text, and then come see me in an office hour. We'll talk about it, or when I present this in class, maybe we can talk about it. Nice. Okay, so mercilessly moving along here, but you can pause at your leisure. What's the next result? There's two more, one for product and one for quotient. So what's the product one say? Well, it says if you take two convergent sequences, so S and T converge, then the product sequence converges, and the limit is the limit of the products. So if you like the poetic version of this, it says that the limit of a product is the product of the limits. And that's all under the assumption, of course, that the individual things converge. It kind of goes without saying. I mean, in a first analysis course, I should be careful and precise, and I shouldn't talk so fast as I am in these videos. But if Sn or Tn didn't converge, then these things don't make any sense. Right? If Sn doesn't converge, then this limit doesn't exist. And I don't know what somebody means by taking a quantity that doesn't exist and multiplying it by a real number or multiplying it by some other quantity that doesn't exist. All right, but here, we're being careful. We've stated that these are both convergent sequences. Okay, so let's have the discussion. So same kind of notation. Let's say Sn goes to S and Tn goes to T. So that's just, I'm calling this limit S and this thing T. So I want to show that the product goes to S times T. So I'm interested in kind of investigating like, well, what's the difference of my sequence and S times T? I want that to be small for sufficiently large N. All right, so how do I get these things involved separately? It was kind of easier in the sum case because all those terms were there, but like I don't have an Sn minus, there's no S in here that's times an Sn or subtracting an Sn. Same for T. So I'm going to kind of give myself what I want. This is sort of a, I don't know, I don't like to use the word trick in mathematics, but it's a method that I'm hoping you're catching on to. I would like to see an Sn minus S. So what I'm going to do is take this difference and kind of put in something. I'm going to subtract S times Tn, because if I factor Tn out of that thing, well, then I have an Sn minus S. Right? But I can't just go subtracting something without paying for it. So I added it back. This minus st was there, and that's kind of a nice fact because if I factor s out of those last two terms, then I got a tn minus t. So I've got them involved. Okay, so very briefly, I'm going to subtract and add that term s times tn, and then just do a little bit of algebra. Factor tn out of the first two terms, factor s out of the second two terms, and use some properties of absolute value in the triangle inequality. Right, factor out the tn and s. Absolute value of a product is the product of the absolute values, and the triangle inequality says that the absolute value of this sum is less than or equal to the sum of the absolute values. Nice. So I'm starting to get a handle on what's going on here because these are the terms that I can control. I can control Sn minus S, meaning I can make it as small as I want if n is big enough. Same for Tn minus T. Okay, but what about these other terms? This Tn and this S, right? Because Sn minus S I can make small, but I'm multiplying it by something times Tn. And if that Tn were getting big, then maybe this isn't small. Over here, no worries. S is some fixed number. Tn minus t is getting small, just kind of like in the previous proof. We'll probably use an epsilon over s, but we just have to worry about what if s is 0. Cool. So how do I say that Tn isn't going to get so big that it's going to ruin the fact that Sn minus S is getting small? I'm going to use the previous section's theorem that Tn is a convergent sequence, so it's bounded, right? It's a bounded sequence. Well, if it's a bounded sequence, that means I can find some number m such that Tn is less than or equal to m for all n. I can bound it. So I'm going to take my inequality that we had up above and say, well, if I replace Tn with something that's greater than or equal to it, I would make the result bigger. Cool. So now I've written out what I've been saying aloud. I can control these two terms. I can make these things as small as I want, right? If this number S is equal to 0, if my sequence Sn converges to 0, then I don't even have to really worry about that term. It's just enough to control the Sn minus S part. Nice. I don't really want to deal with cases here, though. S is equal to 0, S is not equal to 0. We could, being a little bit lazy. So I'm going to do the following. No matter what S is, its absolute value is less than its absolute value plus 1, right? And its absolute value plus 1 is positive. So I'm going to kind of throw that one more thing in here. This number, which I'm going to just underline, I'm going to replace it with something that's not 0. Again, making the result bigger. Because the kind of underlying idea that I'm using here, maybe I should have already said this, that I don't mind making these expressions bigger, because if I can make the expression bigger and that bigger thing is still less than epsilon, well, then the thing I want will be less than epsilon. Okay, so I'm kind of leaving this a little bit fuzzy, but now with those ideas circulating around, maybe you've stopped the video a few times, you've kind of got them in your mind. Let's try to write this proof. So what am I proving? Proving that if you take two convergent sequences, then the limit of their product is the product of the limits. Proven theorem 2.16. So I just restated it here for convenience. Well, copied and pasted it again for your convenience. Okay, modeling some good proof behavior here. Take an arbitrary epsilon. Introducing the notation. Suppose I've got two sequences. Hypothesis says they're convergent. Naming their limits. There exist real numbers S and T, that Sn converges to S and Tn converges to T. That's all, sometimes what I like to call the preamble of the proof. It's saying what the cast of characters are. I've got some sequences, I'm assuming some things about them, they have limits, I'm giving names, and establishing my notation. Cool. Without the discussion, maybe this next sentence seems like out of thin air, but you know where I'm going. Theorem 2.11 says that a convergent sequence is bounded. So there's some number m1 that's some real number that is greater than or equal to Tn for all n. Okay. Without loss of generality, I can assume that m1 is positive. I can always take the bound on a bounded sequence to be positive. Cool. Then again, out of a hat, but you know where it came from, I'm going to let M2 be the limit, capital S is absolute value plus 1. All right. So notice a couple of things. First of all, that S is less than that M2 in absolute value, and M2 is positive, right? Because it's at least 1. Okay, now I'm going to just kind of condition on those things I can control. If Sn goes to S, then I can find some value, capital N1, that makes those sequence terms differ from S by less than epsilon over 2 times N1. It's true as long as I go out past N1. Similarly, I can find an N2 that the T sequence differs from its limit by less than epsilon over 2 times M2. That's true as long as I'm out past N2. So if I take the bigger of those two, the maximum of two natural numbers is a natural number, and if n is bigger than that maximum, then it's bigger than both. So both of these conditions are satisfied. Okay, so putting it all together and using the triangle inequality, my product sequence difference from the product of S and T. I'm not going to really kind of go through all the explanations. I'll just kind of show you the algebra. I add and subtract that term, factor and use the triangle inequality. I replace Tn with its bound M1. S is bounded by M2. And then because n is greater than or equal to capital N, these differences are by definition less than respectively epsilon over 2m1 and epsilon over 2m2. Do the algebra, that's epsilon over 2 plus epsilon over 2, that's epsilon. All right, so that shows by definition that Sn times Tn goes to S times T. So there's the proof. Hopefully the discussion made that proof kind of seem like it's easier to understand. Nice. Okay, one more result, the division statement. Here I'm just going to have the discussion. End this video with an example kind of showing what I mean by using these limit laws, and then we'll call it there. All right, so this time we take two sequences, S and Tn, they're both convergent, and then let's have this little caveat that Tn is never zero, okay? And moreover, not only is Tn never zero, I should have mentioned this before, its limit isn't zero either. Right, because just because Tn isn't zero for all n, that wouldn't mean the limit's not zero. Like here, I can just do a laser pointer example. Those things are not zero for all n, but they approach zero. So this cannot be the case. Can't divide by zero. So let's try to have the discussion. So we got a couple sequences, Sn, Tn. Oops, I switched my lettering here. It's a lowercase for the sequence. Let me fix that. So I've got two sequences, Sn and Tn. Tn is not zero for all n, and the limit isn't zero. And we don't actually have to worry about Sn in general, because Sn over Tn is nothing more than the product of Sn times 1 over Tn, same for the limits, right? We already proved that the limit of the product is the product of the limits. So really, if we can just show that 1 over Tn converges to 1 over T, then we can use what we just did to finish this proof in general. So in other words, without loss of generality, I'm going to assume that Sn is the constant sequence 1. Nice. Okay, so let's take a look at what we need. I want this difference, 1 over Tn and 1 over T, to be small. So I'm going to take a look at what that difference looks like. Well, I got a common denominator, and then I'm going to put the Tn in front of the subtraction in the absolute value. So because this is one of the terms that I can condition on, Tn minus T. All right, so I'm going to use a variant of the triangle inequality. So back from that theorem, I think it was 1.17, that the difference of T and Tn in absolute value is no more than the absolute value of their difference, which again, I can change the order because of the absolute value signs, right? So that's the triangle inequality. Let me just kind of parenthetically, not the kind of vanilla version of it, but a variation of the triangle inequality. I'm just going to write that there for brevity here. And then I'm just solving this thing for Tn. I'll let you check out the algebra. But if we solve that thing for Tn, it says Tn is greater than or equal to T minus that difference, right? But now if I have any positive number, for large enough n, I can make Tn minus T, say, less than the absolute value of T over 2. Because again, T is not 0. So maybe I should kind of write it here somewhere. If T is positive, so is half of it. So I'm kind of using this as my epsilon, if you like, and the convergence statement. All right. So if I return to that inequality, well, the absolute value of Tn is at least as big as this difference. But if Tn minus T is less than epsilon over 2, that's at least as big as T minus it. You should stop and do the algebra at your own pace. But my point is that the absolute value of Tn is at least T over 2. Another way people say this, what I've shown is that for sufficiently large n, because Tn doesn't approach zero, it would be bounded away from zero eventually, right? So I've got this positive number, absolute value of t over 2, and my sequence terms are at least that. So my sequence terms are not getting small. Why am I worried about that? Well, because my sequence terms are in the denominator up here. And if some factor of the denominator is getting small, that's going to influence the ratio to get big. But I don't want this thing to be big. I want it to be small. So that's where this is going to come in. A little bit more subtle here. Okay. So if I just kind of reverse that, if Tn is strictly bigger than t over 2, everywhere you have to read the absolute values, I'm not pronouncing them, then if you reciprocate everything, you reverse the inequality. And again, this would be true for sufficiently large n. This is just the discussion part. So I've bounded away that thing from 0. So the factor up there, 1 over Tn, is small. Nice. Okay, so let me put that in. Maybe I should have revealed this before I said it. So the fraction that I had written above, this thing that's equal to the difference of my 1 over Tn and 1 over t, is no more than, well, I'm just replacing 1 over Tn with 2 times the absolute value of t, but there was another absolute value of t down there, so that's why it's squared, and that's true for sufficiently large n. Stop and verify everything I'm doing. It's hard to kind of follow someone else's speed and thoughts through this stuff, but if you stop and kind of keep looking at the inequalities and do the substitutions, you can fully understand what I'm doing. So what's left remaining here? Well, I've got this Tn minus t, but again, Tn approaches capital T, so I can control that. So I might have to make n bigger. I might have to twice condition on it again, but for sufficiently large n, I can make that difference, Tn minus t, this is very much a strategic choice. I'm going to make it less than t squared times my epsilon over 2. Right? So where is that thing coming from? All I'm doing is I'm kind of going, well, I'd like to multiply by something and get epsilon. So it's this, and that's a positive number. T isn't 0, so its square is not 0. Epsilon was positive. So here's what the algebra looks like. This quantity that I'm trying to make small would be less than, just plug everything in. The product of those two things is epsilon, right? I conditioned on n twice, so I'd have a capital N1, a capital N2. But if I go out past their maximum, just like in the previous proofs, I twice conditioned on that large n, so go out past the maximum of those conditions, and I would get both things true. Okay, so you can try to write this one. I would try to do it. You can also see the proof in your text. I'm going to omit the formal proof from this long lecture. What are we at here? Ooh, 30 minutes, more than 30 minutes. Okay, so let's end it with an example that kind of illustrates like, well, why are we talking about this stuff? What do these limit laws do? Here's an example of a limit that, again, I mean, anybody in calculus can tell you that that limit statement is correct. That rational function in n approaches 1/3 as n goes to infinity. But the algebra to do this with the epsilon n definition, I don't know. I mean, to be perfectly honest, I didn't try it. Maybe it's easy. But I don't want to always go back to that definition if I don't have to, because this thing is made out of pieces by adding and dividing that themselves are all pretty simple. So I'd rather do this using these limit laws. So let me just kind of run through the calculations. Just to kind of prep it a little bit, I'm going to take the fraction and algebraically reorganize it like that. Divide everything by n squared. Okay. And then I'm going to use our properties. Maybe some in this lecture, maybe some from previous homework. N and n squared both go to infinity as n goes to infinity. Those two sequences diverge to infinity. So I think it was one of your homework problems that when a positive sequence diverges to infinity, its reciprocal goes to 0. So 1 over n squared and 1 over n go to 0. Okay. So then the first theorem that we proved says if 1 over n squared goes to 0, well, so does 5 times it. Cool. So that's this term. That term's going to 0. 1 over n's going to 0. 1 over n's going to 0. 1 over n squared's going to 0. So using the sum law, those things in the numerator of this expression, the sum law, I don't remember the name of the theorem. It was the second one, or the number, I mean, the second one in this lecture. This numerator expression approaches, well, the constant sequence has limit 1, this has limit 0, this has limit 0. So this numerator goes to 1 plus 0 plus 0. Likewise, the denominator goes to 3 plus 0 plus 0. All right, that's not equal to 0, it's 3. So the quotient law says the limit of the fraction is the fraction of the limits. So if you roll all of that together, here I cited the numbers. The numerator goes to that sum, the denominator goes to this sum, and theorem 2.17 says the fraction goes to the fraction. All right, so we don't have to always go back. In some sense, indirectly, we're going back to the n epsilon definition. We just sort of did it once and for all with our limit theorems. Okay, that was a lot of material. It's going to take some time to soak in, but I know you can do it. So I'm going to leave it there, and thanks for listening.